So in Chapter 2, we're going to look at the definition of relations and functions. And some of the things that we'll talk about here are concepts that will continue throughout the entire course. We're going to be looking at different types of functions throughout the entire course. You've graphed lines. Lines are functions. We'll look at absolute value functions, quadratic functions, which give us parabolas. There's exponential, logarithmic, rational functions. So this is kind of one of the building blocks of the entire course and everything's going to kind of grow out of here. What are the different functions we could consider and look at? So a few definitions to start out. A relation is just any pairing of x's and y's. So if you take in any data, if you take people's height and weight and pair that, that's a relation. It's a pairing of any two values. Any sort of data, scatter plot, any way that you could get two numbers paired. The domain is the set of the inputs or x values. So when you think of domain, think inputs, think x values. And then the range of a relation or a function is the set of outputs, the y values. So we put a number in from the domain and it spits out a number in the range. A function is a relation. So all functions are relations, not all relations are functions. A function is a relation where each input has exactly one output. So each x goes to only one y. So if I plug in this number, then the only number we get out, or we get a unique number out from that value. So I had mentioned like height and weight. If we took a class worth of people and took everybody's height and weight, so we have maybe somebody that's 5'10", and their weight is 160 pounds. Okay. Do you think that the relation of height to weight is a function? It would not be, because you probably would find somebody else who is 5'10", but would have a different weight. Maybe somebody else that's 5'10" weighs 165 pounds. So this is not a function because there's an input that goes to two different outputs. Now it would be a function if each height only paired with a single weight. So again, a function or relation, it doesn't have to be a graph of a line or a curve or anything like that. We could, here's a relation given just by ordered pairs. So we have pairs of numbers. To draw a mapping diagram, so this is kind of a visual of a relation. We're going to list the numbers in the domain. So the numbers are the domain are the inputs. So the 3, -1, 2, -2, and 0. Those are the numbers in the domain. If you wanted to be a little more organized, you could put those in numerical order. And then we'll also list the numbers in the range. So 2, 0, -1, 1, and 3. 2, so this is the range, 2, 0, -1, 1, and 3. And then we just draw an arrow to map what values go to another. So 3 maps to 2, -1 maps to 0, 2 maps to -1, -2 maps to +1, and 0 maps to 3. So looking at this, we can pretty easily determine if it's a function, and it is a function because each input only goes to one output. Okay, each input goes to one output. Now let's say we had another point that was 3, 0 in this relation. Then that would mean that 3 is also mapping to 0, right? 3 to 2 and 3 to 0. So this is not a function since we have an input going to multiple outputs. So one other quick example, let's say we have a domain of 1, 2, 3, 4, in a range with just 5, and all of those values in the domain map to that single value in the range, is this a function? So does it break the rule that any of the inputs map to more than one output? That holds up. Each input is only going to one output. It's not a unique output for each of them, right? But none of them are going to multiple outputs, so this is a function. So a couple more examples. Something like y equals 3x is a function, because for any value that I put in for x, how many values will I get out? Just 1. So if I plug in 1, then 3 times 1 is 3. The only value that I get out of that function is 3. So each input goes to only one output. So something like this, a line, is a function. Some of the homework problems that you'll have, you'll be told to determine if a relation is a function. So we'll look at this. And drawing a mapping diagram can be helpful. So this first one we have -5, -1, 3, and then 3 again. And those are going to map to 4, 0, -1, and -2. And we have 5 going to 4, -1 going to 0, 3 going to -1, and 3 going to -2. Is that a function? No, it's not a function because of the 3. The 3 is mapping to two different values, right? A shortcut is to just look at and see, do we have anything repeating in the domain? Do we have any repeated x's? We have -5, -1, 3, and then 3 again. So that would tell us, hey, we have an input going to multiple outputs, so that is not a function. So for B, we have -3 going to 5, 0 to 5, 2 to -8, 6 to 1. Do we have any repetitions in the domain? No, each of those are unique, right? -3, 0, 2, and 6. So none of those are repeating and going to more than one value. So this is a function. That is a function. And what would maybe trick you is that we have two values going to 5. But again, it's okay for multiple values to have the same output as long as they only have a single output. When we're looking at a graph, and we want to determine if a graph is a function or not, we'll use what's called the vertical line test. So let's say we have some curve. Right, it could be whatever sort of curve we want. The vertical line test, we take and pass a vertical line across. So I can't do this on the screen, but imagine that I'm sliding a ruler across that graph, holding it vertically. We pass a vertical line across the graph, and at any point, at any time, we're only hitting one point on the graph. That means that for any input on the x-axis, we're only getting one output for y. So that tells us that this is a function. It passes the vertical line test. I'm having a hard time writing right now. Okay. So something like a circle would not pass the vertical line test because there are lots of different times where from a single input, we're hitting multiple outputs. So here we hit 2 points at the same time. So this is not a function because it doesn't pass the vertical line test, because at some input we have more than one output. So for this first chapter, and then much of what you dealt with in Algebra 1, were linear functions. Functions that, when we graph them, they make a line, so we call them linear. And those are any functions that can be written in the form y equals mx plus b, so that's slope-intercept form and is probably familiar to you. So I think some of the problems this section might ask you to decide if a function is linear or not. If it's linear, it fits in this form. We have y equals some constant times x plus or minus some constant. So something like y equals 2x minus 1 that's linear. Or f of x equals negative 3/4 x plus 6, that's linear. Okay, I could try to trick you by doing something like y equals pi x plus 6, and that's still linear because pi is still just some number times x. Okay, so decide if a function is linear. If we have anything else happening to the x besides just multiplying it by a constant, then it is not linear. So here we have x squared. So that is not linear. Or over here we have f of x equals negative 4. We could say that this is 0x minus 4. Does that fit the slope-intercept form? Sure does. If we were to graph it, we would get the horizontal graph of negative 4. So that is linear. But if we have anything else happening to the x, if we have x squared or x cubed, or if there's a square root of x, basically if there's anything funky going on in the equation, then it's probably not linear.